Okay then, so in the last lecture I talked about three topologies: the discrete topology, the indiscrete topology, and the finite closed topology, which can be defined for any set, any non-empty set. And now I want to talk about a specific topology which only really lives on one particular set, but it is extremely important. It's called the Euclidean topology. On the set of real numbers. So I write this scripted R here to represent the set of real numbers. So that's the set we're going to define our topology on. So this is going to be extremely important for a couple of reasons. One is that it's just one of the most reoccurring concepts in maths, is talking about real numbers. And two is that a lot of definitions in point set topology are really generalizations of concepts which apply to the real numbers. So we're going to keep going back to the real numbers, looking at their properties, and then seeing how we can generalize such concepts so that they refer to larger spaces of topological things. So, okay, let's just give a definition of what the Euclidean topology on the real numbers is. So basically, to define a topology, we just have to define the open sets. So what is an open set in this topology? Well, a subset of the real numbers is open in the Euclidean topology when it has the property that for every member of this set, S, we have that there exists a pair of real numbers, A and B, which is such that X is inside the open interval between A and B, and that is a subset of S. So basically we have what this means, this writing here, this just means that A is less than X is less than B. So we've got this kind of neighborhood around this point X, which is contained within our set S. And as long as we can make such a kind of neighborhood around every point in our set S, S is called an open set in the Euclidean topology. So perhaps you can see that we can think of these we can think of the open sets in the Euclidean topology in a simpler kind of way. We can think of them as open intervals, that is things which can be written like this. What this is the set of all, well, I use Y. It's the set of all Y in the real numbers such that A is less than Y is less than B. So that's what's called an open interval. And in fact, an open set in the Euclidean topology is just the union of something which can be made by taking the union of a load of open intervals. So that's another way to think of it. But let's not concern ourselves with that now. Let's just focus on this initial definition here of the Euclidean topology on R. Okay then, well, I've said it's a Euclidean topology on R, although I haven't proved it. So let's now try and prove that this is actually a topology on R. So as usual, I encourage you to pause the video now and see if you can actually prove that this is a topology. Prove that these open sets satisfy the conditions which we were talking about in the previous video. Okay, so let's see if we can show this. So remember, we need three conditions to be met. The first condition is that we want the entire space, which in our case is the real numbers, and the empty set, we want these to be members, well, we want them to be open sets. So clearly, for the set of all real numbers, if you take any point in the set of all real numbers, x, then you can choose a, well, okay, let's say this explicitly. So for all members of the set of real numbers, we can let a equal x minus 1, and then b equal x plus 1, and then we're going to have that x belongs to the open interval between a and b, and that is going to be contained within the set of all real numbers. So that's good. The empty set, that satisfies this property here by default, because it doesn't actually have any members x, so it doesn't have to satisfy these conditions, it just satisfies this condition by default. So the empty set is open. So okay, our so-called open sets satisfy condition 1 of our three conditions necessary. What about condition 2? Maybe I'll delete this to make a bit more space. Okay then. So condition 2. This is that we want to show that the union of any collection of open sets is open. Okay, so this is really easy. So let's just suppose we've got some so let A be a set of open sets, and so now for every member of this set A, in other words for every open set in this collection, and for every member of this open set, since S is an open set here, we're going to have this condition holding, that there exists AB such that X belongs to this open interval AB, which is a subset of S. And since it's a subset of S, it must also be a subset of the union over all S belonging to A of S itself. And so what we've essentially shown here is that for our sort of generic point here, X, we've found an A and B, which is a kind of neighborhood which contains X, which is inside this union over all these open sets in A. So essentially this shows now that the union of any collection of open sets is open. So we've got point 2. So finally we want to show that point 3 is satisfied. Remember, point 3 was that the intersection of any pair of open sets is open. Well, actually, we could equivalently have that the intersection of any finite number of open sets is open, but you can easily show that the second thing holds from the first condition. So let's just prove the first condition because it's simpler. So we want to prove condition 3, which is that for any pair of open sets, I guess I'll call them S, well, let's write it a bit better, for open sets S and S prime, we want to show that the intersection of S and S prime is also an open set. So how are we going to do that? Well, basically we want to show that, again, we can find one of these special neighborhoods within any point, around any point within the intersection of S and S dash. So how do we do that? Well, we're going to let I don't know what's going on here. Let X be a point in the intersection of S and S dash. That's most peculiar. Anyway, let X be a point in the intersection of S and X dash. Now, since X belongs to S, and S is open, that means that there's going to exist A and B such that X belongs to A and B, which is a subset of S. Also, by similar logic, since X belongs to S dash, there must exist A dash and B dash, which are real numbers, such that X belongs to the open interval between A dash and B dash, which is a subset of S dash. So now it must follow that X belongs to the maximum, it belongs to the interval between the maximum of A and A dash and the minimum of B and B dash. And that, a little bit of thought should convince you that that is actually a subset of the intersection of S and S dash. And so that completes the proof, because we've found for our generic point x, we've found our kind of neighborhood of it, which is contained within the entire set. So that shows that the intersection of these two generic open sets is open, and so we've shown points 1, 2, and 3 hold, and therefore we've proved that this is actually truly a topology on the set of real numbers. So in general, an open interval is just written in the form Rs, and this is equal to the set of all real numbers such that R is less than X less than S. So it's the round brackets that make it an open interval. And there are other kinds of open intervals as well. In particular, you've got R infinity. So let's talk about these two things. Rs, that's the set of all reals between R and S. R infinity, that's a set of all reals which are greater than R, which go all the way up to infinity. Of course, they never actually get to infinity. And another one is minus infinity R. So these are all different kinds of open intervals, and I'll leave it as an exercise for you to prove that each of these is an open set within the by the definition from the Euclidean topology which I just gave you. Okay, so now let's talk about closed intervals. So we write closed intervals with square brackets. So for reals c less than d, we write square bracket c comma d to denote the closed interval, and this is just equal to the set of all real numbers which are greater than or equal to c and less than or equal to d. So there we have it. This is a closed interval. So we want to prove some things about closed intervals in the Euclidean topology on the real numbers. So our first proposition is that the closed interval CD is not open within the Euclidean topology on the real numbers. So let's do a proof of this. We shall do a proof by contradiction. So suppose instead that C comma D is open, and now we're going to find a contradiction. So how is this going to go? Well, we're going to take well, if this is in fact open, then we're going to have that we're going to be able to find one of these open intervals around each point within this set, which is contained within the set. So in particular, this implies that there's going to exist A, B, such that this point C, which is in our set, is going to belong to the open interval between A and B, and this open interval will be contained within our closed interval C comma D, if it is indeed an open set. which actually it isn't, but we're looking for a contradiction. So now we're basically encroaching on our contradiction, because you should hopefully see that this statement here is really kind of implying some contradictions. But let's flesh it out and see exactly where the problems are. So in particular, let's think about the implications of this bit here. What does this imply? Well, on the face of it, it says that A is less than C is less than B. And that implies that A is less than the average of A and C, which is less than B. Sorry, which is less than C, which is less than B. Okay, so what does this mean? Well, it has a couple of important implications. It means that the average of A and C is a member of our open interval AB, and also the average of A and C is not a member of our closed interval between C and D. And so we've found a point which belongs to AB, but it doesn't belong to CD. And so what that means is that AB is not contained within CD. And this directly contradicts this statement here. That's contradicted now. So we started by assuming that this is an open set, and we've reached a contradiction. And so our initial assumption must have been wrong, and it must have in fact been that C, D is not an open set. So that's a proof by contradiction that closed intervals are not open sets. Okay then, so we've shown that the closed sets are not open. Okay then, so we've shown that closed intervals are not open. Now let's show that closed intervals are actually closed sets in the Euclidean topology. So this is more straightforward. So we want to show that the closed interval C, D is closed on R. And again, when I say on R, I mean within the Euclidean topology defined on R. That's what I mean whenever I don't explicitly specify topology when I'm talking about the real numbers R. Okay, so what's the proof to this? Well, the proof is very simple. Maybe you'd like to pause the video and see if you can figure out the proof for yourself. Basically, remember that a set is closed if its complement is open. So what's the complement of C, D? Well, let's write that down. Well, it's equal to the open set, the open interval from minus infinity to C, in union with the open interval from D to positive infinity. And these are both open intervals. And as I was saying before, they're both open sets. But I might as well prove it explicitly. So, in particular, suppose we have a point a generic point x belonging to d comma infinity. So in that case, we can set a equal to d, and we can set b equals infinity, and then we're going to have that x belongs to ab. Oh, sorry, we don't want b equal to infinity. B is equal to x plus 1 will suffice. No need to go so big. And so in this case, AB is contained within D infinity. And so there we have it. We've managed to find a kind of open set containing our generic point x, which itself is contained within the set of points between D and infinity. So that shows that this set of points between D and infinity is an open set. Almost completely the same kind of proof can show that the set of points between negative infinity and C is an open set. So the union of the two is an open set, and this is the complement of the closed interval C comma D. So C comma D must be a closed set. That's the end of the proof. And so here are some more important points about the Euclidean topology. So one is that every singleton is a closed set. Okay, so the proof to this is really quite similar to the one we've just seen. In particular, the proof is simply that the complement of this set here is this, which is clearly an open set. So that means that the original thing must have been closed. Okay, so we can use more of this kind of logic to prove another important fact. So by scripted Z, we denote the set of all integers. Okay, so this is a set of all integers, positive and negative from 0. And so Z is closed. In the Euclidean topology upon R. So here we're thinking of Z as a subset of R, where R has a Euclidean topology. So how are we going to show that this is a closed set? Well, it's a pretty similar strategy to the one we've been using before. What is the complement of a set of integers? Well, it's fairly easy to write. The complement is equal to the union where our integers go from minus infinity to infinity of the open interval between n and n plus 1. And so this is the union of open sets. So it is open. And since this is open, since the complement of Z is open, Z must be closed. Okay, so another really interesting aspect of the Euclidean topology has to do with the rational numbers. So we denote the set of rational numbers by a kind of scripted Q. So this denotes the set of rational numbers. Which are the numbers of the form a divided by b, such that a and b are integers. And the interesting fact is that the set of all rational numbers is neither open nor closed. In the Euclidean topology upon R. So it's a fairly interesting thing, and I shall just leave that as an exercise to you to prove it. So good luck with that one.